In this video, we're going to discuss colligative properties, kind of collective properties of materials in solutions. So on top of molarities and weight percents, talking about how much stuff is in solution, if you have things in solution, you actually change the properties of the liquid. So pure water on its own will have a boiling point, a freezing point, and a behavior. But if you dissolve things in it, that solution, despite mostly still being water, changes its properties. And so what are those changes? How does dissolving materials in solution affect its behavior? First and foremost, let's talk about freezing point. When a liquid, which is fairly loose, kind of stacked together, freely kind of flows around itself, when a liquid begins to solidify, all the little parts have to start to align. They need to take a recurring pattern to make a nice crystal, to make a solid. To do this, as they cool down, they just don't have the energy to keep rolling, and they end up sticking to each other, and they collapse into these solids. Well, if you have some large object in the way, it doesn't have to be large, just something that isn't water, some other thing. What happens is it starts displacing the rows. They can't align quite as well as they're supposed to. Because there are out of position water molecules, well, this means the attractive forces between the molecules isn't ideal. Their angles are wrong, their distances are wrong. They just don't hold on to each other quite as well as they would in a normal solid structure. Around something that is dissolved in solution, your molecules for the liquid cannot align quite as well into a solid as they would if that object was not there. So a sodium ion, a chloride ion, phosphate ion, a sugar molecule, whatever is there, it interrupts the ability to attract water molecules to each other. Well, the whole idea to freeze is you've got to be able to hold on to the nearby water molecules. So if you cannot hold on as tightly, it's easier for them to break free. You have to be even colder before they will get stuck in place. They have to lose some energy, go even slower before they'll get frozen. And so by having anything in solution, you lower the freezing point. This is why salt can de-ice walkways. If you have a lot of water and it's frozen, just a little bit on the surface, you throw the rock salt on it. As the sun hits it, the very surface does melt briefly from the sunlight. That dissolves some of the salt, and in that little bit of water that's on the surface, now there's a massive amount of salt. That water can't refreeze. So it begins to flow and rolls off the path. The ice re-exposes, the sunlight hits it again, it melts a little bit, it dissolves some of those rock salts, cannot refreeze, and slowly it will just clear the ice off the path. This is why we salt roads, this is why we salt paths, this is what the salt is doing that allows us to prevent ice accumulation. Now this only works so well if you've lived somewhere where it can get really cold. You may have noticed that salting the path at some point just doesn't work anymore. If it is cold enough, despite having lots of salt, it will still freeze, because there's an equation for it. The change in the temperature of freezing is equal to a constant of freezing. So this is a change that's unique to every liquid. Different liquids will have different amounts of temperature that they'll change depending on how much is dissolved, and a slightly different unit, molality. Italic big M, molality, is moles of solute over kilograms of solvent. So instead of being a volume-based concentration, it is a weight of solvent concentration. This is because your volume actually changes as your temperature changes. Water and the like will expand slightly as they get warmer and shrink as they get colder. As a result, if you have a 1 liter bottle of 1 molar solution at room temp, and you bring it up to near boiling, well, the same amount of stuff is there, but it's expanded in size. It might be 1.1 liters now. So the same number of moles in a slightly larger volume makes the concentration look less. Molarity is temperature dependent, but molality is not. And so we have to use it when we want to do these temperature calculations. So let's just take a quick look at water. Well, 1 liter of water is just about 1 kilogram. So let's say I have a 1 molar solution. That's just about 1 molal at room temp. And so we'll start with that. And even if the molarity changes as we cool it down, the molality will not. And so if I have 1 mole of my chemical in 1 kilogram of water, I can go over to the formula and say, hey, I have a 1 molal solution. Well, how much will that change my temperature by? Kf for water is negative 1.86 degrees Celsius per molal. So 1.86 degrees Celsius per molal times 1 molal. So my change in temperature of freezing is 1.86 degrees Celsius. Now, it goes down, so it is that much less than the original solution. Water is originally 0. It's going to lose 1.86 degrees Celsius for a new freezing point of negative 1.86 degrees Celsius. That 1 mole of a chemical in a kilogram of water will reduce the freezing point by approximately 1.8 degrees. If you had a 2 molal solution, it'd be twice this. If you had a 4 molal solution, it'd be 4 times this. There's a practical limit. You can only get so much stuff to dissolve, and the colder you are, the harder it is to get things to dissolve. But you can press down the temperature of water's freezing by quite a lot. In fact, this is why Fahrenheit is 32 degrees when water freezes. Pure water freezes at that temperature, but the coldest you can get water is very briny salt in the Arctic. And so there is well below freezing liquid water as long as there's lots of salt in it. And so that is 32 degrees lower in Fahrenheit, and that's why 0 Fahrenheit was set at the coldest we could find any water. It just happened to be very salt-rich water.